Today we will learn about quadrature amplitude modulation, or usually we call it QAM. So sometimes you will see QAM written in the text, or quadrature amplitude modulation. Initially we will discuss the concept of this modulation scheme. It is an M-ary digital modulation scheme, an M-ary digital modulation scheme. M-ary digital modulation scheme, and you are familiar that this m is actually an integer which is equal to t raised to the power k, right? And k is 1 2 up to capital M, right? So k varies from not up to capital M. K varies from 1 to and so on. It's an integer. So you have this is an M-ary digital modulation scheme, and we will see its mathematical representation first. We'll see how to mathematically represent QAM symbol or QAM signal. Then we will provide a proof for the symbol energy. This is actually the symbol energy represented by E sub I bar. This is the average symbol energy. This is the average symbol energy. So we'll discuss about the average symbol energy of quadrature amplitude modulation. We will see the expression to find out this average symbol energy. Similarly, we will find out the mathematical expression for the average power. So this is our average power. Once we find the energy, then we can easily find the average power of the signal. We will move forward to learn quadrature amplitude modulation signal constellation, QAM signal constellation, and then our next topic will be QAM modulator. So let's start with the QAM modulation. Before actually going to the mathematical expression of QAM modulation, let me recall your previous knowledge, as you are familiar with the the two modulation scheme. The first one is pulse amplitude modulation, right? Pulse amplitude modulation, and the next one is phase. This is the amplitude modulation, and the other one is phase shift keying, or the phase modulation. I should say the phase modulation. So you are familiar with these two schemes from your previous lectures. So if you go back to your previous lectures, we represented PM signal. We represented PM signal in a generalized form, such as AI. We said that this is the mathematical expression for our PM signal because of omega ct. So we have in the amplitude modulation, or the pulse amplitude modulated signal varies or differs from another pulse amplitude modulated symbol or signal by the amplitude AI. So each symbol in a PAM, this is actually a PM modulated signal. We are discussing PM here. So each PM symbol differs from another symbol by the amplitude AI, or if I say this, and you are familiar with this I, that it varies from it is from 1 to m. So it is actually an M-ary modulation scheme. So each SI differs from SJ. Another, that is I and J are from these from I and J are one of these numbers where I is not equal to J, right? So each SI differs from SJ by amplitude AI in PM symbols. So this is unique for each symbol SI. Similarly, if you observe the mathematical expression of the PSK, phase shift keying, or the phase modulation, we said that our signal, the phase modulated signal, the phase shift keying, in which we learned the BPSK and QPSK actually, we said that our signal SI differs from the from another symbol by the angle theta I, right? So this is an expression. This is an expression for PSK signal. Again, your I is the same as given here above, from 1 to capital M. So you have an M-ary PSK modulated signal, and M-ary PSK modulated signal, each SI differs from SJ by theta, angle theta. Now we saw that in amplitude in the PM signal is a one-dimensional signal. This is what we know from our previous knowledge, that PM signal is actually a one-dimensional signal. It is a one-dimensional signal. When we say one-dimensional signal, it means we can draw our signals. We just need one basis function psi 1 of t to represent our signals, and we have seen that in PM signals all the signal points lie over here, right, in just one dimension. So we have all the signal points in one dimension only, right? 4, 5, 6, 7, and let me try it 8 signal points, and let me erase this one just not to be so we have, if suppose we have 8 signal points here, so in this case I have m equal to 8, and all the 8 signal points are placed on the psi 1 axis. They are placed on the psi 1 axis. While in PSK, or phase shift keying, our signals are two-dimensional. It means we need two axes, psi 1 of t and psi 2 of t, to represent our signal points, and you can represent your signal points in these dimensions. The simple example is QPSK. So M-ary, we learned about M-ary PSK, right? MPSK. The simplest example is QPSK when m is equal to 4, and your m is equal to 4, and we said that okay, we have this signal constellation. Now with having this knowledge from our previous lectures, if you observe that your signal, now let me recall psi 1 of t and psi 2 of t. If you just recall your signals psi 1 of t, we said that our psi 1 of t is 2 over t cos of omega ct, right? And psi 2 of t is minus under root 2 over t sine of omega ct, right? And we already know the negative sign which is placed over here. This negative sign is purposely placed over here to facilitate our mathematical expression in the QAM symbol which we discussed in QPSK. We can just write the QPSK signals as a summation of psi 1 and psi 2. So we place here a negative sign. Now with this knowledge, another useful identity which actually we are going to use today will be about the you see the another useful identity is about the you will see another useful identity which is the Euler identity, e raised to the power j theta, and you are familiar that this is equal to cos of theta plus j sine of theta. So we may use this identity today. And another mathematical formula, cos of alpha plus beta, which is actually equal to cos of alpha cos of beta minus sine alpha sine beta. So you know these mathematical identities, trigonometric identities, which we will use today in my lectures. So with this knowledge, let's go ahead to see how we can represent mathematically the QAM signal. But let me clearly mention that when we say QAM signal, when we say QAM quadrature amplitude modulated signal, this is also coherence amplitude phase key, or it is, let me write it, amplitude phase key. Amplitude phase key. Why we call it amplitude phase key? The reason is the variation of amplitude, as well as phase in this signal, in the amplitude and phase variation for each signal. So we will see that actually each signal or each symbol in each QAM modulated signal, each QAM, this is QAM modulated signal, each QAM modulated signal, actually each QAM modulated signal is identified by a pair of amplitude I and an angle theta I. So each QAM symbol will have a unique pair, So we will see that actually the amplitude and phase variation, both these amplitude and phase variation, the amplitude and phase variation when combined, when we combine these amplitude and phase variation, the signal SI of t of the QAM modulated signal is formed. So QAM is so we conclude that QAM is actually QAM is also known as the amplitude phase key. So we will see shortly that the mathematical expression for a QAM is a combination of the mathematical expression for the amplitude PM and the PSK, pulse amplitude modulation, and the phase shift keying. Well, mathematically we represent our signal Si of t as a in this form. Let me write it out, and then we will discuss these variation E sub I over t, P of t, and we have cos of omega ct plus theta I. So if you observe this expression, we have for each I the amplitude, the energy of the signal is E sub I, and its phase is theta I. It means we have if you open it up, right, applying that trigonometric identity, you can, or let me write it here first in more compact form. AI, I can write it AI P of t and cos of 2 pi f ct plus theta I. So we can rewrite it in this form. Now we have each SI of t has a unique amplitude and phase, and you are familiar with this P of t, which is just a pulse between 0 to t with a unity amplitude, right? It's a pulse from 0 to t with a unity amplitude. So if you draw your P of t, you are familiar that this is a pulse from 0 to t with amplitude plus 1. It's a time axis, right? So it means this our Si of t is actually confined to this interval 0 to t. So our Si of t is just present in this interval 0 to t. Now we should note here that each symbol Si of t is different from Sj of t. Each symbol Si of t is different from Sj of t, where just keep this in mind that we are talking about I not equal to j, which means that different symbols, right? And just to recall here in this expression, our I is from 1 up to capital M. We have an M-ary QAM signal. This is an expression for M-ary QAM signal. So when we say I not equal to j, it means if I is equal to 1, j cannot be equal to 1. J may be 2 or any other value. So each Si of t is different from Sj of t by this pair, Ai and theta I. So this pair, actually this is important, this pair is different, unique. This pair is unique for each symbol Si. And we later on see that when identifying or detecting the QAM signal, we would actually try to identify this unique pair, because this is how we see that by these symbols are different. Where these symbols differ by the Ai. Now Ai and theta I, right? The amplitude and the phase. So each Si has a unique amplitude Ai and theta I. Now if you recall your concept of your concept if you recall your concept of signal space, you we can just we can rewrite our si of t let me rewrite it, which is ai cos of omega ct plus theta I, and for a complete description you should mention that I is from 1 up to capital M and time is between 0 to capital T. So this is the QAM symbol. Now we should be able to write this QAM symbol as a linear summation, as a summation of psi 1 and psi 2. You can clearly see from this expression. If you use that mathematical identity, you can write it cos of omega ct cos of theta I plus sine of omega ct and sine theta I, right? So if you use this trigonometric identity, you can rewrite your expression as ai cos theta I, and you have cos omega ct, which is carrier, right? And similarly you have ai sine theta I, and you have sine of omega ct. So now if you observe closely, this is these are two carriers at a frequency fc. So we have two carriers at frequency fc, and these are two sinusoids, two orthogonal carriers. Why we say two orthogonal carriers? Now you should know at this stage that when we say orthogonal carriers, it means the linear the dot product of these two signals would give you 0. So the dot product of these two signals would give you 0. Now we should be able to write it as a linear combination of psi 1 and psi 2. So I earlier mentioned that our psi 1 is equal to under root 2 cos omega c 2 over t cos omega ct, and psi 2 also is given above. So if I just directly write it in this form as psi 1 of 2 plus si 2 psi 2 of 2 psi 2 of t, this is my symbol si of t. So our QAM symbol is a linear combination of si 1 and si 2, which you can observe from the above expression. Now you should be able to derive si1. So if you just try to find out your si1, just rewrite, and you will rewrite the value of a, rewrite this value of a, right, ai here, and you will see that your si1 is actually equal to under root e sub I cos of theta I, right? And your si2 s sub I2, this equals under root ei sine theta I. Now you can verify this. You can easily verify this. Just compare these two equations, this one and this one, and you can find out these S sub I1 and S sub I2, and you should be familiar with this S sub I1 and S sub I2, that these are actually the images of the signal Si over this is the image of this signal Si over psi1 of t, right? So it is the image. This S sub I1 is the image over psi1, and similarly S sub I2 is the image of the signal, image of Si of t over psi2 of t. So now this should be clear right now, because we always observe our signal in the Euclidean space, or we say signal space. So if you observe your signal in the signal space, you can identify these. You can just say that, okay, my Si1 and Si2, which are these values, may be positive or negative. So we have just because we said that our signal Si of t, which is a QAM modulated signal, is a linear combination of Si1 and Si2. So it means that we can draw our signal in the Euclidean space using psi1 of t and psi2 of t as the two axes, and some point over here or anywhere in this space which has Si1 and Si2 the two coordinates. This point over here represent the QAM modulated signal, right? So well, you can also say that this signal constellation we have seen earlier, and this is for QPSK. So that is also, it's true, it's for QPSK, and this signal, this is having the same amplitude, right? All these 4 points have the same amplitude. So this QPSK, or we also say that for QAM when m is equal to 4, right? M is equal to 4. It is the same as the QPSK signaling scheme. It is the same as the QPSK quadrature phase shifting signaling scheme. But higher values such as M8, 16, then it differs from the PSK, because then you have multiple amplitudes. You will see that some amplitudes here, like these signal points. Now we have different these. If you observe these 4 signals, they have different amplitude than these inner ones, right? So we can represent our signal in 2 dimension, and we saw it from this expression of our QAM signal. So now we are interested to find out the energy of our signal, right? So it's quite easy. You can when we are interested in energy of our signal, signal I, and what we do to find out the energy, we integrate our signal, we integrate the square of our signal, right? So we will have the same procedure for all of our signals. So let's try to integrate, substitute this value, and our signal is only present from 0 to t, so the limits change from 0 to capital T, right? And if you integrate it, the square of the signal, which is AI square, and you have p square t and cos square omega ct plus theta, right? So this was AI p of t cos. So we are just squaring that expression, or even if I write over here, suppose, so let me okay, this is okay, dt. Let me erase these limits, and I'll tell you another point here. Let me erase these limits. You can put it plus minus. Now minus infinity to plus infinity. Now if you observe, this p of t exists only from 0 to t. So it means this whole product exists from 0 to t, and the rest, the product is, for the rest of the time the product is 0. Now your limit automatically changes from 0 to capital T, and from 0 to capital T, this is 1 square, right? P of t is p square t is actually the square of the 1 is square of unity is unity. So you are left with ai square and cos square. Cos square can be written as 1 plus cos of 2 omega ct plus theta I over 2, right? And dt. So we have this integral. We have this integral. Now from here, if you go ahead and try to integrate this out, what do you get? We have an integral. Let me write it in the form of two integrals, 0 to 2 dt, and another integral is again ai square over 2, 0 to capital T cos of 2 omega ct plus 2 theta, right? dt. So we have this dt, right? So this is the integral which we have to solve. Keep in mind whatever is the phase angle, whatever is this phase angle, if you integrate this waveform from 0 to capital T, you will get 0. A sine wave over a period, whether it has 2 cycles, 3 cycles, 4 m or 100 cycles in that period, you will get 0. This you can verify from your Octave or MATLAB as well. So this integral gives you 0. These integrals give you 0. You will be left with this integral only, right? You will be left with this integral only, and here it is ai square over 2. Now if you do not now here I assume, if you keep this in mind, here I assume that the energy of this is unity, right? If you say that no, the energy is not unity, then what will happen? If you say that okay, if you are not sure whether the energy is unity or not, so actually what happens, your integral here, if you see this integral here, it's not just dt, it is actually p square t and dt, right? Instead of dt, you would get p square t dt. Now this p square t dt, what is this? This is the energy of the pulse square. You are integrating the square of the signal in that interval, and this is the energy of the pulse, which we assumed to be unity. So our expression, the energy of our signal, the expression for energy of our signal is to be more general, it is this one, right? This one. So we say that okay, this is the energy, this is the energy of the ith signal. This is the energy of the ith signal. So any of the M-ary signals, any of the M signals, or any of the M signals will have this energy. Now if we try to find out the average energy, now the average is always, how do you find the average? Just sum all and divide by the total number of the symbols. So if we have 4 symbols, sum of all the 4 energies of all the 4 symbols divided by 4. If you have 8 symbols, right, you can have M equal to 4, 8, 16, right, 256, right, 512, 512 and so on. So you have many of these symbols. So 256, 512, many. So these quadrature amplitude modulation QAM signaling scheme is supported in 4G, and you can have any of these values of M. Well, some of the M values are supported, not all. I have seen some which we can discuss later on. So the average QAM symbol energy, if I am interested in the average energy, this is the energy of the ith symbol. If you are interested in the average energy, so we said that the average energy is the let me write the change this notation. The average energy, I would use bold letter to represent the expectation. The average energy is equal to the expectation of the expectation of the symbol energy EI. It is the expectation. This bold E represents the expectation or the mean value, the average value. So the average value is this one. Now if you compute it from this, because you already have the EI, so you can say that okay, my average is actually equal to the expectation, right? So the expectation of let me take my pen back. The expectation of AI square over 2 E EP, right? So or EI square over 2 EP. Now we are just writing it from our above expression. Now this can be rewritten. This can be rewritten in the form of you can just say that okay, it is half energy of the pulse. It's energy, right? Constant, 2 constant. So it comes outside the expectation, and then you have the expected value. You have the expected value of actually the expected value of, we say, AI square, right? We have the expected value of A, because this AI changes for different symbols. So whatever the symbols you have to find out these. Each will have different AI. EP is constant for each symbol, right? So this can be expressed as half energy of the pulse, and then we can write AI square bar. So this bar represents the average value. So this is the average symbol energy. This is the representation of the average QAM symbol energy. Average QAM symbol energy. We can write it average QAM symbol energy. So it's a representation of average QAM symbol energy. Now if you have the expression for the average symbol energy, you can always write the expression for the average power, and we say that okay, our average power can be expressed as the average energy over the time interval. So the average energy per symbol divided by T, this gives you the average power. right? Average power expression. Sometimes you may see SI over here, so it's the same thing. So if you see SI, it's the average symbol energy, for the average symbol energy. So we have the average symbol power. So notation should not confuse you, right? So you should be able to know this now. So this is our average power. Average. We say this is our average power, or the expression for the average power of QAM symbol. Okay, we move forward to QAM Constellation. So if we see our QAM signal, so let me start from here. Now we are actually in we want to know the QAM Constellation. QAM Constellation. So let's move to the QAM Constellation. We saw that we can represent our signal as I of t as SI1 of t plus S sub I2 psi 2 of t. Right? This is the representation of our QAM symbol. Now it means that each symbol SI, each symbol SI, now I write it bold just to represent the vector, right? So each symbol SI has a unique pair of SI1 and SI2. It has a unique pair of SI1. This is the vector representation. This is how we say vector representation. Vector representation of QAM signal. Vector representation of QAM symbol. Or QAM signal. It's a vector representation of QAM signal, or QAM signal. Let me write it. QAM signal or symbol. So it means your QAM symbol actually can be represented in 2 dimensions, because you have two unique x and y coordinates, right? So you need an x-axis, x and y-axis. So if you observe your signal constellation, for a QAM, you should have 2 axes. Now there are 3 major types of QAM signaling scheme or QAM constellation. If you observe the type 1 constellation, which was actually type 1 constellation was used in 1962, sometimes 60s or 1960s actually. It was discovered that we can have this arrangement in 2 circles, right? In 2 circles we can arrange our signal in 2 circles where you have signals, QAM signals here. Now you keep in mind, this is I1 of t and this one is I2 of t. So you have these points, you have these signal points, 8 on the outer circle. Similarly you have 8 signal points on the inner circle. So this constellation was used for transmission in 1960s, which was known as type 1 QAM constellation. It was known as type 1 QAM constellation, right? Type 1 QAM constellation. Well, soon after the use of this signal constellation, another type of type 2 constellation was used, and it was proved that this is better than type 1 constellation. Its performance is better. Let's observe this type 1 constellation. Let's observe this type 1 constellation, and we can see that there are like all these the points, signal points on the outer circle has this phasor, right? This vector, outer circle, and the length of this vector is same for all of these points which are on the outer circle. Length of the vector is actually the length of the vector represents the square root of the energy, right? The length of the vector is the square root of the energy. So this energy, it means this energy is greater than the energy which is for these inner signal points. So we have all the 8 points on the outer circle has a different energy which are greater than all the 8 points which are on the inner circle, which are on this inner circle. They have less energy. You can always find the coordinates here if some parameters are given. For example, here this is pi by 4, right? Pi by 4, 45 degrees, pi by 4 radian, 45 degrees. So when you say 45 degrees, you can find out the signal point, these coordinates, right? 45 degrees, so you can find out these coordinates. So we have the psi 1 and psi 2, or we also say that this is the I channel and this is the Q channel. This is the I channel and Q channel, right? The in-phase channel and the quadrature channel, right? So these are all the signal points. If you observe any signal point, for example this one, it has two components along I axis and along Q, along I channel and along Q channel. So it has two rectangular components. You will see the importance of these rectangular components. So each signal point has two rectangular components. Similarly, the type 2 constellation, which was just after the type 1 constellation, which was used soon after this one, just a year after this one, they used the same two circles, but instead of placing 8 points on the inner circle, they placed just 4 points on the inner circle, so that the distance between these points is increased. If you compare it with the previous diagram, if you see the previous diagram, these points are close together. These, let me encircle the points. These points, let me encircle these points, right? These are closer to each other. So the more closer the points are, we call it Euclidean distance. If the Euclidean distance, the distance between the adjacent points, if the Euclidean distance is less, they are more prone to errors, right? So what actually in the next type of constellation, what was proposed, that instead of packing the inner circle with 8 points, pack it with 4 points. Pack it with 4 points and place other points here on the outer circle, and instead of putting just 1 point, place 2 points here, which are still far apart, and these points, now we have 12 points at the outer circle. If you count it, we have 12 points at the outer circle. So these 12 points at the outer circle, if you find the Euclidean distance of these points. Now the Euclidean distance here is the average Euclidean distance of this constellation, which is known as type 2 constellation. Type 2 constellation. This is known as type 2 constellation. So the average Euclidean distance, the distance between the adjacent points, average Euclidean distance for this constellation is greater. It is, the average Euclidean distance is greater than the Euclidean distance of type 1 constellation. So this Euclidean distance is greater as compared to type 1 constellation, right? And the more Euclidean, the more you far apart these signal points are, it's more better for it has more immunity against the noise, against the white noise. So better for transmission, better for communication. So this was proved that it is better than the type 1 QAM constellation. Well, in 4G, none of these two are these two constellations are followed. In 4G, the constellation which is actually followed has the signal points. It has the signal points which are which is known as the square QAM, or the signal points are just like this square. These are the signal points. These are the. Now each of these constellation has 16 points, so it is 16 QAM, right? Type 1, type 2, type 3, type 4. Each of these have 16 points, so it's 16 QAM. This one is known as the square QAM signal constellation. If you see, you have the energy of these points which are on this square, they have the same energy, right? You can prove this, that the energy of these signal points is same. Similarly, you have another square. You have another square. You can say that if you observe, we can just draw this square. You can just draw this square here. Right? We have another square. Right? So this is actually a square QAM, or we say QAM constellation, or it's also known as square QAM. Square QAM constellation. Square QAM constellation. Right? So this is the third type 3 constellation, which is actually used in it is used in 4G as well, supported in 4G. And we have I and Q channel, these orthogonal channels, and it is easy to observe that any signal points has two unique components, right? One along I axis, one along Q axis. I component and Q component. Each signal point has two unique components. Now, if you observe the I channel, if you just concentrate on the I channel, this one, right? You have 4 unique amplitudes. This amplitude, this amplitude, this amplitude, and this amplitude. So I channel is actually PM modulated, you can say. I channel is PM modulated channel. Similarly, if you observe the Q channel, now if you concentrate on the Q channel, let me choose a different color. So if you concentrate on the Q channel, which is this one, again you have just 4 amplitudes. See, these 4 amplitudes. So Q channel is also a PM modulated channel. So what actually this is with this knowledge, you can easily see that each signal point is just a summation of, it is a each signal point SI of t can be observed as a summation. It can be observed as a summation, of two, PAM modulated or is a summation of two orthogonal PM modulated carriers. Right? Two orthogonal. Let me specifically write two orthogonal PM modulated carriers at FC, right? At FC, same frequency. So sine of 2 pi fc, cos of 2 pi fc, and both are just PM modulated carriers. So it's superposition of two PM modulated carriers. When you add them up, you get a QAM symbol. So the ease of implementation can be observed from this. We conclude that it is easier to implement this square QAM symbol as compared to other types, because you just need PM modulated carriers and you just add those carriers to get a QAM modulated signal. Now, with this knowledge, if you observe if you want to find out the magnitude of SI, or the magnitude, the mod of SI, which is actually the energy of the signal, right? And you can easily verify that this is actually equal to SI1 square plus SI2 square, right? This is the energy of the signal. This is the square root of the energy, right? So you have the energy of the signal as the sum of these two components. We have already, I hope you can verify this expression now, because you can write your QAM symbol in this form, SI2 of t, right? And when you square and integrate this SIT square dt from 0 to t, which is the energy of this signal EI. If you square and integrate, you just end up with this expression that this is actually equal to SI1 square plus SI2 square. I proved it in one of my previous lectures, I guess, while discussing QPSK. I proved that this is actually equal to the summation, this one. And if you observe it from the signal constellation diagram, you see there, you can say that, okay, your signal, suppose this is your QM symbol, right? And it has two components, SI1 and SI2. So you are familiar with the Pythagoras theorem, right? You are familiar with the Pythagoras theorem. This square is equal to the square of the base square of the perpendicular. So if this is your point, you have d square, which is equal to b square plus p square, and you can always find d. You can always find d, which is actually the square root of b square and base and perpendicular square. So here, if you observe your base, it is this one, SI1, right? This point is SI1 0, right? And this point is SI0, SI2. So this is your perpendicular, right? This is the base. So you can say that your base is actually SI1, and when the square of the base perpendicular is actually equal to SI2, square of the perpendicular. So you can see that your signal. Here the magnitude is actually equal to, or we say that, okay, our signal magnitude SI mod is equal to square root of SI1 plus SI1 plus SI2, and we have verified it earlier that this is actually equal to the square root of the energy of the signal. The average symbol energy, now you can find if you are interested in the average symbol energy, same procedure. If you are interested in the average symbol energy, which we represent by E sub I bar, this bar is for average. So the average symbol energy is actually equal to the expectation. He said that this is equal to the expectation. Let me choose my marker. So this is actually equal to the expectation of EI. It is actually equal to the expectation of EI, which means just sum all the symbol energies of all symbols and divided by the total number. So you will get the average symbol energy. It's the mean value, expected value, the average value. So you can also rewrite it. You can rewrite it in this form. But okay, our average symbol energy is actually equal to let me write there in the form of SI. So this is actually equal to mod SI, right? This one. So we keep this in mind. Square now. I have written square because that's the square root of the energy, right? From here, square root. So the energy is the square, SI square. Now, if you want to find out this phase, these SI, we can easily find out the phase angle, and the phase is tangent inverse SI2 over SI1. You can see from that figure, SI2 over SI1. From here we have this signal point, right? So just don't forget your Pythagoras theorem. This is your theta. So SI1, SI2, and this theta of course is equal to tangent inverse this side over base, tangent inverse of SI2 over SI1, right? SI2 over SI1. So tangent inverse SI2 over SI1. So this is your theta, and you can always find the Euclidean distance between two signal points. If you have two signal points SI and SJ, and you are interested to find out the Euclidean distance between these 2 points, right? Again, the Euclidean distance can be found by the expression for Euclidean distance, which is the mod of point SI minus SJ. These are the signal points in the these are the signal points of the Euclidean space, right? So when you try to find out this, again, if you see, this is nothing but this expression here, this expression. So if you have 2 points, how you get this one? I think this should be clear, but let me write it for you. Suppose you have 2 points, right? You have 2 points. Let me draw 2 points first. You have 2 points here and here in the space, in this space, any 2 points. You want to find out this distance. So what this is SI and this is SJ, right? SI and SJ. So how do you find this SI? You can always you can always you have 2 points for 2 signal points, x1 and y1, right? And you have x2, y2, x2 and you have x2 and y2, right? These are the 2 points, x2, y2, x1, y1. So how can you find this distance? This distance is given by the square of the distance. Actually, the square of the distance is equal to what? The square of this distance ij is equal to x2 minus x1 whole square plus y2 minus y1 whole square. We are familiar with this expression, I hope. So so if you are you are familiar with this expression, we are using the same. This is from your elementary classes, right? Here's from your elementary class. So here we are actually using the same expression. When we say dij, we have 2 signal points, and we use the same expression that, okay, we have si1 minus sj1, right? si1 minus sj1 square plus si2 minus sj2 square, right? So this is our distance. We will find our Euclidean distance using this expression. And what is ij? It should be clear. Ij is from 1 to capital. Ij is from 1 to n. So this is actually ij, 1 to n. So for M-ary, QAM symbol, we have ij from 1 to capital M. So this is the Euclidean distance. The formula, the expression for Euclidean distance between the signal points. So you can find these Euclidean distance if you know si1, sj1, si2, sj2. So first of all, you need to identify where these points, what are the coordinates of these points in the space, and then you can find out the Euclidean distance. Keep in mind, the more the Euclidean distance means a better constellation. The signal points are far away from, they are at more Euclidean distance from one another, and when they are far from the adjacent symbols, they are less, they have more immunity against white noise, or less prone to noise effects. So we'll see the QAM modulator. We will discuss the modulator in the next slide, next video.